In this example, let's solve this very interesting instance of the heat equation. What I have drawn here is the initial condition. So we're in one dimension on the segment from 0 to 1, a situation that we've encountered before. And so this example will parallel the one example that we've already solved for the heat equation. It's just that with this one, there are a few interesting things to say, and we will actually compute the answer. We'll calculate the infinite series and see what the answer looks like. Whereas before, we stopped at the closed form infinite sum and called that a solution. So here's what's interesting about the problem. I'm considering this initial condition. I'll state the boundary conditions in a second. So what you can imagine this being is a room where it's warm on the right, from your point of view, warm, I was right the first time, warm on the right and cold on the left. So maybe it's a really cold day and the radiator is over there. The other way around. It's cold over there and the radiator is over there. And then imagine that somebody instantly turns off the radiator. So that other wall gets just as cold as that wall. So our boundary conditions will be 0 on the boundary. And you might say, rightfully so, that there is a problem to begin with, because our initial condition doesn't match the boundary condition. How can this function have the value of a at x equals 1 at the initial instant, but then for all times greater than 0, be right at 0? And so all I can say is two things. That number one, this won't really prove to be a problem. You can make this rigorous by saying that the differential condition only needs to be satisfied in the interior and not on the boundary. And so this will definitely be a singular point. But so what? There is one point where there is a problem. So I'm being vague about it, but what I'm trying to say is we'll make it work. But the more important point is that when it comes to PDEs, it's very much an art. There is never a prescription that works for all situations. You have to approach every situation and ask yourself, does it make sense? Can I make sense out of it? Can I find solutions that satisfy in a certain sense, right? When there is a glaring inconsistency like this. And you always have to think about what problem did it come with? Can I make sense of it in that situation? What do I expect to happen to the discontinuity? Does the discontinuity go away instantly? Or does the discontinuity persist? In which case, I'm now studying the discontinuity, which scientists do all the time. It's one of the most interesting categories of problems, called shock waves. So shock waves are all about equations not like this, where discontinuities, as you're about to see, disappear, but where a discontinuity persists. And you can say, well, how can we even solve a problem like that if there's a discontinuity on the one hand and derivatives on the other? How can you take the derivative of something that has a discontinuity? Well, you approach it in a creative way. That's where opportunity for creativity and input comes in, and your original thoughts. So, but at the same time, it has to be rigorous and mathematically sensible. So what happens in that case? You break the domain into two domains, to the right of the discontinuity and to the left of the discontinuity, and it makes perfect sense on either side. So you just now have to state something on the boundary. And so you state an initial condition that governs where that boundary between the two smooth regions is and how it evolves. And that's how you study that. So there's always opportunity for making sense of what's going on. And what do we expect here? Let's just think about what do we expect here. We kind of know the problem this came with, the problem where this equation came from. We all know the problem this equation came from. The temperature was at equilibrium. It was cold there, warm there, nice, smooth, in-between type of curve in between. And then all of a sudden somebody turned that off, so immediately it gets a little bit colder there, and then that cold begins to propagate, and then finally overtakes the whole room, and it's going to be 0 everywhere because it's 0 at the wall. So after a certain period of time, it'll be 0 everywhere. So that's what we expect. So let's see if we actually get this if we pursue our standard recipe. And our standard recipe is to decompose the initial condition into a Fourier series in terms of signs. We could do it in the complex sense, but let's just stick to signs. They work just as well here. Multiply each one of them by e to the minus alpha eigenvalue times t, and add them all together. Each eigenvector from in the separated spatial equation gets multiplied by the appropriate decay coefficient factor. So I think that's correct. So all that's left is to program it. And I won't even rely on my integration genie. I'll just let Mathematica do all of the work. All right, are you guys prepared? Let's do it. Okay, here we go. We will first need our coefficients. Where am I? Okay, so can you see it, or should I go one down? C. C as a function of n is the integrate a times x. Well, let's say that a equals 1. A times x times sine of n pi x, where x goes from 0 to 1. And I think the whole thing has a coefficient of what? 1. Wasn't it 1? 1. I believe it was 1. 1. We're going to stick with 1. Okay, let's take a look at that answer. There we go. Looks familiar? It sure does. But we actually don't care what it is. So I'll suppress the output. Now we have to say that u of x and time is the sum of the same thing of, c of n times the corresponding sine times exponential of minus alpha, alpha equals 1 as well, e to the minus alpha times n squared times pi squared t. Am I right? From 1 to, well, we'll just go with 10 terms first. We have to be pragmatic. I don't think we can do infinity, because I don't think this is the sort of series that you can add in closed form. So it won't help, at least from the intermediate point of view. And here's the answer. So it will be a long sum, but here it is. Okay, so this is the series. So all that's left is to plot it. So let's plot it. So again, once again, I'll suppress the output and I'll say plot u. You know what? We usually make t the first variable, right? So let's stick to it. Tx. So u, let's first plot it at time t equals 0. And we're sure to see the Gibbs phenomenon because we only have 10 terms. Well, you'll see the Gibbs phenomenon with any number of finite terms, but this will be quite vivid. This is at time 0. From x from 0 to 1. And here's what it looks like at the initial moment. Do you recognize our initial condition? Except it's the first 10 Fourier series of our initial condition. It'll get much better if I go to 100 terms. And there's the Gibbs phenomenon. And you see how it drops down to 0? You should think about what is it that makes it drop down to 0. We've talked about it. It's the average between two limits. Okay, let's see if I can handle 1,000 terms. Not bad, right? So do you see this very characteristic Gibbs phenomenon? Let me make it a little larger. I think I can do it. I think I remember how to do it. Plot style, thick. Did it get better? Okay, so what happens in the Gibbs phenomenon is that the segment that's affected gets narrower and narrower, I believe linearly with n. But the height stays constant at about 18% of the discontinuity. So this is about 1/5 of the jump, right? So this continues periodically here, and so it goes. So this is the amount of the jump right here. And I guess this is about 20% of it. So that's how the Gibbs phenomenon works. So analytically, when you go to infinity, you have this perfect straight line. But if you limit yourself to any finite number of terms, you have to deal with this Gibbs phenomenon. Yes? And it's 0.5. So I think we're missing a coefficient of 2 somewhere. Where? In the C sub n?
Oh, it's 2. It's you're integrating, because remember the whole thing that we flip around this.
Yeah, that's right. It's twice the integral. That's right. Okay, so it's the thing we talked about in the earlier video. We're integrating from -1 to 1, but we're actually integrating that anti-symmetric continuation. Very good catch, Preetham. Okay, now we're at 1, right? Okay, so there you go. So now let's actually see the evolution as time changes. So for that, all you need to do is take this same thing and say manipulate. With t varying from 0, well, let's go up to 5 seconds. Okay, and now instead of 0, I can put in t here. Okay, let's not do 1,000 terms. You guys are with me on that, right? Okay, so here it is. And what this gives me the capability of doing is dragging this lever and changing t. So here's t at 0. Right, so that's our initial condition. Use your imagination to do away with the Gibbs phenomenon. And here's what happens at later times. And it's actually diminishing, so you're not seeing because the axis keeps rescaling itself. So let me fix that. It goes in here, plot range. So in the x direction, it can be automatic. And in the y direction, let's go from 0 to 1. Okay, same picture. And here we go. Make sense? And then it's very quickly at 0. So we can actually go to 1.
Probably does it.
Well, it depends on alpha. But yes. So one question for which I don't have an explanation, or maybe I do. Why does it become symmetric more quickly than it goes to 0? So do you see right here, it's already symmetric between left and right. It starts totally asymmetric, and then very quickly becomes symmetric, and then goes down to 0 as a symmetric function with respect to the center. I don't quite have an explanation for that. Actually, I do. And you will also notice that the Gibbs phenomenon disappears very quickly, right? You certainly see it at time t equals 0, and then it immediately disappears. So why is that? So both can be explained the same way. So the reason the Gibbs phenomenon is there so strongly is because in the Fourier series for AX, the coefficients decay very, very slowly. They decay only as 1 over n. And that's what causes the Gibbs phenomenon. But when we put together the solution, we multiply them by a decaying exponential. And as soon as t is not equal to 0, when t is 0, this is 1. But as soon as t is not 0, this is instantly a decaying function as a function of n, exponentially decayed. And so the function becomes infinitely smooth, basically instantly, after one moment. For any non-zero t, we now have an exponential decay in coefficients. Instead of 1 over n, they're now decaying exponentially. And so by definition, there is no Gibbs phenomenon. And this is very characteristic of the heat equation and something that you should know, that the heat equation makes discontinuities disappear instantly. That's why it's often called the diffusion equation. So, and the Laplacian, when its first time derivative equals something proportional to the Laplacian, we'll see it in fluids as well next time. It's called diffusion, and the Laplacian is called the diffusion term. And when diffusion is present, discontinuities disappear instantly from the analytical point of view. And to answer the first question that I asked, why does it become symmetric relatively quickly? And by symmetric, I mean now it's kind of a symmetric shape. Well, it's because everything but the fundamental sign, the first sign, dies much more quickly. So what we see after half a second, I don't know what we're at here, but something like half a second, all we're really seeing is the first sign, the lowest sign, dominating, because it decays the slowest. The second sign decays 4 times as fast, and the next one 9 times as fast in the exponent. So very, very quickly. So that's why it becomes symmetric. So really a simple explanation, the same as with a guitar string. Doesn't matter where you pluck it. Initially, you hear that, so if you want a sharper sound, you will pluck it further away from the center. But after that initial attack, you really can't tell any longer how the string was plucked. So that's kind of what we're seeing here as well.